The purpose of this activity is to introduce to you the two systems used in astronomy in determining the position of a celestial object such as a star. The two systems are the horizon system and the equatorial system. The horizon system measures the position of a celestial object is at the sky at a given time. This is done by using the coordinates altitude and azimuth. If an object is straight overhead like this here, its altitude is 90 degrees and it is said to be at the zenith. The great horizontal circle on which the sky seems to be sitting, the great horizontal circle like this on which the sky seems to be sitting, is the horizon. Now, altitudes are measured by drawing a great circle centered at the center of the earth and intersects both the zenith and the object whose position is to be measured. So that great circle, which is centered at the center of the earth, and altitude is measured from the horizon to the object. This angle is the altitude. All right? So the altitude of an object at the zenith is 90 degrees. Azimuth is the angle measured along the horizon starting from the north direction, measured clockwise. So azimuth is the angle measured along the horizon clockwise from north to the point at which the great circle intersects the horizon. This is the great circle intersecting the horizon here. So the azimuth is measured from the north direction, measured clockwise to the point of intersection of the great circle and the horizon. Azimuth goes from 0 to 360 degrees. 0 degrees at the north, 90 degrees at the east, 180 degrees south, and coming back to 360 degrees at the north. Now, altitude and azimuth are changing constantly with the rotation of the Earth. As the Earth rotates, these coordinates are continuously changing. It also changes from location to location on the Earth. Therefore, it is useful to have a coordinate system that locates the position of stars and planets relative to each other, which does not change with the rotation of the Earth or position on the Earth. Now, such a system is called the equatorial system. Now, to introduce the equatorial system, first of all, I have to introduce the concept of the celestial sphere. Now, what is a celestial sphere? A celestial sphere is an imaginary sphere. See, look at the Earth there. And if you stand at the Earth, you can imagine a sphere that is surrounding the Earth that contains all the celestial objects. So all objects in the observable sky can be thought as projected upon the inside space of the celestial sphere. Now, Earth has an equator. That's the equator of the Earth. If you project that Earth's equator onto the celestial sphere, you get the celestial equator. So you need to understand the concept of celestial equator. Celestial equator is the projection of the Earth's equator onto the celestial sphere. The celestial sphere has a north celestial pole and a south celestial pole. Now, in order to locate a point like the position of a star on the celestial sphere, we draw a great circle. Now, we draw a great circle from pole to pole. Look at that. And that great circle passes through the star whose position we need to find. That is the great circle. Now, this great circle is called the hour circle. And if you notice here, the hour circle intersects the celestial equator. Look at that. That's the celestial equator. We talked about it. The hour circle intersects the celestial equator at a point called the foot. And the most important point that we need to consider here is the vernal equinox. As the sun goes around the earth, on March 21st, the sun will cross the celestial equator at this point. That is the point called vernal equinox. The sun will then go down south. It will then move like that and then cross the celestial equator again. And then move north, come here, and that's the way the path of the sun around the earth occurs. So vernal equinox is the position at which the presumably sun's path crosses the celestial equator. Now, this is the starting position for our measurements. So the origin in this coordinate system is the vernal equinox, the position of the sun on March 21st, when the path of the sun called the ecliptic intersects the celestial equator. That's the vernal equinox. We measure the angular distance eastward from the vernal equinox in degrees. We measure the angular distance eastward from the vernal equinox, but this time we are not measuring the angular distance in degrees but in hours. Now, how is that possible? Now remember, as the earth rotates, one complete rotation occurs in 24 hours. So the position goes from here, that is 0 hour, 1 hour, 2 hour, 3 hour, 4 hour, and so on up to 24 hours. So we measure the angular distance in hours, minutes, and seconds. So we measure the angular distance eastward from vernal equinox, remember, not in degrees again, but in hours, minutes, and seconds. This angular measure from the vernal equinox to the foot, that is measured in hours, minutes, and seconds, is called the right ascension of the object. That is the first coordinate, the right ascension. How do you measure the right ascension? First of all, you should understand the hour circle. Hour circle is the great circle that passes through the north celestial pole, the south celestial pole, and the object whose position is to be determined. And that great circle intersects the celestial equator at the point called foot. Now, right ascension is measured from vernal equinox eastward, and measured in hours, minutes, and seconds. So this is the right ascension of the star. How many hours, how many minutes, and how many seconds. Now, the second coordinate in the system, equatorial system, is the declination. Declination is this angle. How do you measure that? It is measured from the foot to the object whose position is to be determined along the great circle. And that, of course, is measured in degrees. So right ascension is measured in hours, minutes, and seconds. Declination is measured in degrees